In this section, I'm going to take a look at a few of the functions that Linux provides that can help us with process synchronization. Now these are going to be pretty simple. They're actually going to be a lot easier than what you might expect. The first stuff to look at is the atomic operations. Now in terms of the Linux kernel, right, most of the stuff is basically going to focus on something that looks like an integer, right? So it's basically this stuff up here. The idea is, right, is that there's this custom type defined atomic underscore t, which is basically going to be our atomic integer, right? And over this integer, all various things expressed, right? So we'll have our set, add, sub, inc, read, right? We have kind of these 5 different things here. All of these, right, we can basically just assume that all these operations, right, are going to happen atomically. Now, underneath the hood, right, how is it implemented? We don't really know, right? I mean, it's going to be different based on what version of the kernel we're on, right? Or if we're on a different OS, right? Maybe things are similar but implemented in a different way. Typically, these things, though, under the hood, right, they're implemented with one of those hardware synchronization features we talked about earlier, like test and set, right, or compare and solve, something like that. The point is, right, kind of at a top level view, right, in terms of Linux, right, we basically have this idea of, oh, you can basically atomically handle, right, some integer, right? And then from that, you can hopefully build other things like semaphores and mutexes, whatever it is that you want. So it's a relatively straightforward API here. We're not really going to need to use it, though, because it's nice to use, higher level constructs instead. There's other stuff available, right? Spinlocks, right, we want to stay away from. That's the idea, right? Kind of busy waiting, right, and just having a while loop that waits forever. But then the last one there, right, which is kind of more important to us, right, is basically the idea of mutexes, and that I have a little bit of a code sample in the next slide. That's pretty simple though, right? It's basically, can I initialize one? Can I lock it? Can I basically unlock it, right? It's not too bad. Let's go ahead and jump forward to the slide that has that example. So you can see here on the left side, this is basically the most simple example you could ever construct of a mutex. So you can see this, right, first of all, we need basically, our header file, right, in order to bring in all the threading stuff. So we'll bring in pthreads, right, the standard library. Then we create our mutex variable, right, and this is really our variable that somehow represents that mutex resource, right, that one thing that's kind of floating around out there, right, we try to lock it or, maybe we unlock it, right. So that's kind of the heart of everything. And then we have basically our initialization. So I'll set up our mutex. The first argument, right, is basically just a variable that, tracks the mutex that we create, right. The second parameter there is for attributes. If you need to have special settings for mutex, you can pass them over here where the null is. They'll take an attribute setting struct. For now, right, we can basically just leave it alone and just create a mutex, it's fine. Then we have our code basically to acquire the mutex, right, or release the mutex. So here, right, we have our basically our pthread mutex lock. So point at the variable, lock it, right. Now here what this is, right, this is a blocking command. So if I'm running my code, right, and I do this lock, right, on this variable, right, and the variable indicates the mutex isn't currently available, I'll just sit around, right. So I'll actually wait for that variable basically to become free, me to acquire a lock, right, before I jump down and run basically the critical section code down here, right. So that is a blocking command. So let's say I acquire it, right, I do my stuff, right, I'm done, then I do my unlock, right. So I do my unlock, right. Obviously that's not going to be blocking because I can always do an unlock because, basically at that point in time, right, I know I'm going to be holding mutex, so of course I can release it. So release the mutex back, right, and then I can go on and do my other stuff. So really it's not too bad, at all. The other example here, right, is for semaphore, right. So that's the other thing we talked about, a little bit more complexity than a mutex. So here, right, we'll bring a slightly different header, right, so bring in the semaphore header instead. Create a semaphore variable, right, again to track basically that semaphore. And we can initialize it, right? So this is our initialization. Initialization looks a little bit different than it does for mutexes. First difference, right, is that I have basically this value here at the end, which represents what it is that I want to start the semaphore as. Now, one of the big differences between a mutex and a semaphore is simply the idea of, a semaphore, right, can have, basically any number in there, right? A mutex is I either have it or I don't have it. A semaphore is basically counting, right? They call it, typically it's called a counting semaphore. I mean, there's also binary semaphore as well, but we're using it for, right, basically a counting semaphore, saying, okay, I can put in any number I want. So if I want to, I can put 5 or 15 or whatever I want in that little space. For now, I've just put 1 to indicate there's basically, one resource that semaphore has, kind of hidden or locked away. So that's the first difference. The second difference, right, is this middle parameter here. This middle parameter, well, it isn't too important. Basically what that is a visibility modifier to say who can see the semaphore or not. Usually you leave that as 0 because a 0 means that any thread that's associated with your current process has visibility and has scope to basically use this semaphore. So that's typically what you want. All right, so a little bit more difficult, a little bit more different there. Okay, so other code, right, is pretty much the same, right? So I have a semaphore wait, right? Semaphore post, right? So that's basically my lock, right, and then my release. They match up just the same, right, as the mutex functionality. Take the one argument. It's pretty straightforward. And then in between, right, we have a critical section, right? So there we go. That's kind of the semaphore syntax, right? So it's really not that bad for using semaphores and mutexes. Well, I should say the code isn't that hard. Really what ends up being more problematic is when you actually need to come up with the logic, right? They can actually, rely on these things, right? They can actually do work, right? So logic is harder. All right, so let's move along.